All right. So it's been so long since we did this that I'm actually gonna test. All right, that we're gonna just rederive and remember what the heck all this code is, because this was the code to simulate the double pendulum, but okay. So let's just remember we have 2 point masses, and we need to figure out which each have their own length, and each point mass has its own mass. Now, we need to figure out to determine the Lagrangian, which is determined by the potential and the kinetic energy minus the potential energy. So the kinetic energy of the system is the kinetic energy of the, and let's look at the double pendulum, is going to be right, exactly, because we get 1/2 mv squared. I don't know what this is. Why is it that the kinetic energy would not be just 1/2 mv squared, where v is equal to the sum? Because then you would get 1/2 m1 v1 squared plus 1/2 m2 v2 squared. But it's not. You have plus this I is probably the moment of inertia. And wait, and because the thing is, I'm so bad at mechanics. I don't know how I'm so bad at mechanics, but I am. Let's figure out why is it 1/2 mv squared again? It has to do with F equals ma. In Newtonian mechanics, the kinetic... Okay, yeah, right. In Newtonian mechanics, the kinetic energy K of a particle is defined as the work required to accelerate it from rest to speed v. Okay, so that's always the thing, is remember the definition of kinetic energy. Kinetic energy is defined as amount of work. So it's got units of work, which are joules. Required to accelerate a particle of mass m to speed v. Okay, so if m is constant, we get F equals ma is the force is equal to the mass times the acceleration. Right, a force is a mass times an acceleration. okay, is equal to m dv dt is equal to mv dot. By the way, guys, big news. I switched to 1 millimeter G2 pens. I got 2 of them, and I like them. I also got 0.5. Don't like them. I like that the bigger ones are smoother because you're depositing more ink, I think. All right. And an infinitesimal displacement is dx equal to v dt. Since v is equal to dx dt, dx is equal to v dt. This made more sense the last time. Thus, the infinitesimal work is the change, an infinitesimal change in the work So dW is equal to mv dv. We integrate both sides and we get W is equal to 1/2 mv squared. Okay, so the work was the amount of almost like, so like, I guess the thing to remember is that work is a quantity. I always got to go back to this. So first we got newtons. So newtons is equal to what? Kilogram meters per second squared. Because it's the amount of, this will give me Isaac Newton. It is the amount, it is the force that accelerates 1 kg at 1 meter per second squared. So if I push with 1 Newton, 1 kilogram, it's going to be, in the first second, it's going to be going 1 meter a second, and then it's going to be going 2 meters a second. And I'm applying that force constantly, right? So that's how the acceleration happens. Now, we go to joule, right? And joule is, right, joule is kilogram meters squared per second squared. By the way, guys, this is a very cool way to think about unit systems in general. So I was just asking GPT this. You can think of the dimensions of a unit system just as an abelian group over the integers, basically where each dimension has its own index, and the integer at that position is, you know, like if you have a 2 in the first position of this list of 7 numbers, that means it's like kilograms squared, or like seconds squared. And if it's negative, it's obviously 1 over seconds, so you get hertz or something. But I thought that was cool because nobody ever tells you to think about it as a abelian group. All right. Over dimensions, not over specific units, but over the dimensions of the SI units, because there are 7, 1, 2, 3, 4, 5, 6, 7. So there's mass, time, or wait, distance, time, mass. NA is interesting because NA is literally just an integer, right? Candela. How is candela defined? Because I asked my professor, I was like, okay, we're going down a crazy rabbit hole. I just kind of wanted to know. But I've always loved the SI unit system. It's just very beautiful. Okay, so the joule is the amount of work. So this is the unit of work. And the Newton is the unit of force. Okay, and what it is it's applying, it's the amount of work done when a force of 1 Newton is applied, displaces a body through a distance of 1 meter. Displaces a body through a distance of 1 meter. So if I have a kilogram block and I accelerate it, so it's at rest and I accelerate it to 1 meter per second, so we have a kilogram block and it's at rest on a frictionless table, and I start pushing on it with 1 Newton of force, and then I let go after 1 meter. Okay, and then what is a watt? Now a watt is kilogram meters squared seconds cubed. So this is power. This is the unit of power. It's 1 joule per second. Okay, so now that we've done a units thing and we've remembered what kinetic energy is, now we need to go and figure out what is potential energy. Because potential energy is the next quantity that we need. Oops. Oh, this is all kind of coming back to me. Conservative and non-conservative physics. Right. Okay. Um, okay, so the potential energy is also so the kinetic, and that's the only way that the kinetic minus potential would work, and potential energy are quantities of work. Okay, so let's just remember that if we have a single pendulum pointing straight up, oh right, and here's where we get into coordinate systems and how we denote our origin, because the nice way to denote the origin is at the holster, or whatever holds the double pendulums at this point. So if we have, let's just talk about a single pendulum. So this, so if we have L is the distance of the pendulum, then it pointing straight up has a distance of 2L from its rest position. So rest positions are going to be 0 minus L1 and 0 minus L2. Oh, no. Minus L1 plus L2. Okay. Those are our rest positions. Now, my understanding is that the amount of potential energy is basically the amount of work that it took to lift that, and it's conservative. I forget why. It probably works out to just how the integration is done. But if I, for instance, if I lift this pen in this path versus this path, it doesn't actually change the potential energy. Right. So I can take any path, but to raise it that amount of height is the same amount of work. Now, of course, it's not actually, because, like, literally how much work it takes me to move this is different. So, like, okay, wait. Let's just clarify that with a little chat. For potential energy, why, if I move a pen up 1 meter straight up versus arced, is it at the same potential energy? Right? Okay. All right. That's enough for me. We can't keep going down the rabbit holes because we actually need to finish the project. But I'm happy enough with that explanation. So then the potential energy, so let's say we're at so remember that our phase space is theta 1 and theta 2. These are our state variables, and they're described from straight up and down. Okay. So we have, so then the distance, all right, yeah, so let's hop on that TL draw. I probably already have the exact same thing still open. Oh, this is terrible. I thought I had a bunch of stuff. Oh, that's cool. Okay, how do I... Okay. Okay, so then the position of this first pendulum in X and Y is going to be... Okay, so then... its position is going to be... So then I think the position should be... let's check my work. So x1 is equal to L1 sine... Yes, that's actually true. This is x. This is the x direction. This is x1, and this is y1. And yeah, right, because this is positive and this is negative. So this is going to be minus. But then the distance between, so how far it's been lifted, so the delta y is going to be equal to L minus or we could write it more simply, L1 minus cos theta 1. So this is how much it's been lifted. So this is, so then if we want to know the potential, if we want the potential, then it's going to be mgh. It's going to be m times the force of gravity, so this is m1, times the force of gravity times delta y 1. Okay. So there's how we get that. And now we can see here, this is nice. Okay, right. And then for the second pendulum, bro, I've thought so much about pendulums. It's crazy. Compared to, I mean, I'm sure that some people spent their entire lives just thinking about pendulums. But over this past whatever, I've thought a lot about pendulums. Okay. So the next thing we want to do is now we want to figure out, so now we have the positions of x1 and y1. And I remember, we're just re-deriving all this because you can look at these expressions and be like, yeah, but unless I draw the picture, I just keep forgetting. All right, so now we have our second pendulum to deal with. L2, theta 2. Okay, so from x1 and x2, we're going to get a nested thing. So x2, okay, so x2 we understand is just going to be x1 plus L2 sine theta 2. And y2 is equal to y1 plus minus L2 cos theta 2. Great. Cool. So now we have the positions in Cartesian form, but they're, I mean, sort of in Cartesian form, but it's still, the expression itself is still written entirely in terms of angles, which is what we want because if you, which is what we want. Okay, so now let's get to the Lagrangian. So what is the kinetic energy on the first pendulum? The kinetic energy is the amount of work required to accelerate a particle of mass m from rest to speed v, if m is constant. So we want the velocity so it should be, yeah, the square root of the sum squared of dx1 plus dy1. So if we get v1 is equal to square root of dx1 squared plus dy1 squared. Okay, so, but now I want to know, is that true? Because the equations of motion here, why is this 1/2? Dude, Firefox does this stupid thing. Oh, yes, that's exactly what I wanted to do, you idiots. Firefox is a joke of a browser. All right. Yes. Okay. Oh, yeah, that's right. So wait, hold on. We need to take into account that x1 dot is going to be equal to d dt of L sine theta 1, which is equal to L cos theta 1 times theta 1 dot, and y1 dot is equal to minus, oh wait. The minus cancels out and it becomes L cos theta 1 dot. Oh wait, L sine. Okay. So then the speed squared, yeah, so then v squared is equal to y1 dot squared plus x1 dot squared. Oh, if you full simplify this, what the hell's going on? Why isn't it working? Okay, but let's just simplify it manually. So this becomes L cos theta theta dot squared plus L sine theta 1 theta dot all squared. Okay, so we get L squared plus cos Okay, so we get so if we factor out L squared theta dot squared, we get cos theta squared plus sine squared theta is equal to 1. This goes to 1. So then we just get L squared theta dot squared. So that's the velocity. So then why do they have this extra thing here? I think that this is because, honestly, this whole article is pretty dumb because they don't even describe what that is. The first term is the linear kinetic energy of the center of mass. And the second term is the rotational kinetic energy around the center of mass of each rod. So I guess they describe it, but not really. Oh yes, wait, so we get, so mg delta y becomes mg times L times 1 minus cos theta, which is equal to, mgl 1 minus cos theta. Okay, cool. So we get the potential. So the Lagrangian is just going to be, right, so this is equal to v squared. Yeah, so this is v squared. So then K kinetic is equal to 1/2 mass times L squared theta dot squared. So then L for single pendulum, L single, is equal to 1/2 ml squared theta dot squared minus mgl 1 minus cos theta. And actually the masses can be divided out, right? or at least factored out. Yeah, you can't divide them out, but you can factor them out. So you just factor them out to be. So m times 1/2 L, or actually we can factor out ml, 1/2 L theta dot squared minus g 1 minus cos theta. All right, that's the Lagrangian of the single pendulum. All right, we'll do the equations of motion. Okay, so all right, we can do the equations of motion. That's fine. So now we apply EL to L single to get. So first off, this is L. We take d dt of partial of L with respect to theta dot minus the partial of L with respect to theta. Okay, so d dt, wait, show oh, it's actually such a beautiful day. I haven't gone on a hike in so long, bro. I need to go on a hike. Okay. So, first we compute partial of L with respect to the velocities. And we should get 2L squared theta dot or not 2, yeah, because the 1/2 cancels. So you just get m L squared theta dot. Cool. Now you do d dt is equal to right, m L squared theta double dot. Now we compute dl d theta, and that's going to be equal to, so this is going to be so we have minus mgl plus mgl cos theta. So this becomes minus mgl sine theta. Okay, so then the full EL equations become ml squared theta double dot is plus mgl sine theta is equal to 0. So then we actually do get to cancel out the m's and an l, and we get L theta double dot is equal to minus G sine theta. So theta double dot equals minus G over L sine theta. Cool. All right, so we just derived the single pendulum using Euler-Lagrange. Now we want to do the double pendulum Euler-Lagrange derivation. So let's just rewrite down what we had. We had a drawing. Yeah, that's fine. Actually, I hate this drawing. We want to do it like this. Okay. So now what we have is x1 is equal to L1 sine theta 1. And actually, let's be more explicit. It's theta 1 of t, because that's the dependent variable. And y1 is equal to minus L1 cos theta 1 of t. x2 is equal to x1 plus L2 sine theta 2 of t. And y2 is equal to y1 minus L2 cos theta 2 of t. All right, so we've now understood these 4 lines. And we also have x1 dot is equal to L1 cos theta 1 of t times theta 1 prime of t. Or let's do dots. Let's be consistent here. y2 is equal to L1 sine theta 1 of t theta 1 prime of t. Okay, then x2 prime should be this. x2 prime should actually be equal to x1 prime plus the second part. So dx2 we get, yes. So then this is just going to be x2 prime, x2 dot is equal to x1 prime plus L2, yeah, L2 cos theta 2 of t theta 2 dot of t. Y dot 2 is equal to y1 dot plus, this is going to be a plus, it's going to be L2 sine theta 2 of t theta 2 dot of t. Great. Okay, so now what we want to know is the kinetic energy. The velocity of m1 is 1/2 m1 v1 squared, where v1 is equal to, where v1 squared is going to be equal to x dot 1 squared plus x or y1 dot squared, right? It's the sum of the velocities. Okay. Oh, and there you go. Is that what we had? I'm pretty sure that's what we had. Yes. Great. Which ends up equaling L1 squared theta 1 dot of t squared. Okay, great. Now it's time to figure out what the velocity is. Is that true though, that the velocity is just like this? Good, 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 good. Dude, it's writing all of this stuff I'm writing. Now V2, this is what I wanted to know. Okay, so V2 squared, we can apply the same for mass 2's velocity equal to, so V2 squared is equal to x dot 2 squared plus y dot 2 squared. Since okay, great. So that is the total kinetic energy. So then let's just clarify though that in this one, I think I might take mechanics, honestly. Mechanics is so cool. I really do like classical mechanics. Okay, so then uh, so for a system of point masses, now to find the potential energy. the amount of work to raise from rest against gravity. So wait, mg1, hold on. mgy1, let's just derive it ourselves. So we know that we expect the distance from rest is going to be, so we have so if we have, so it should be L minus cos theta 1L, which is equal to, oh wait, L minus L cos, yeah, so we're going to get L times 1 minus cos theta 1 of t. This is the, this is what I call delta y1. Okay, so then, okay, so the potential for the first pendulum is m1g L1 1 minus cos theta 1 of t. Right, we already did that. We already derived that, but I'm a little slow. Okay, so now we want to know the potential for the second mass. Second mass potential. Right, so we have y2. Is that right? Yes, that's right. Yeah, y2 bottom. Oh, interesting. Right, yeah. Because, like, for instance, if we have... I'm gonna go plug in my phone. So it should just be... Compute the vertical rise is going to be y2. y2... Cos, cos pi is equal to minus L1 over root 2 plus L. Okay, great. All right. So, indeed, y2 is equal to y2. So delta y2 is equal to y2 minus L1 . Wait, actually, didn't I have it the other way around? Okay, cool. So this is equal to just L1, 1 minus cos theta 1, plus L2, 1 minus cos theta 2. All right, great. So now we have the potential energy is just going to be, so second potential is equal to M2G delta Y2. Is that what I had? U1. Wait, oh, this is not what I want. K1, K2, K, P1 for potential, MG, Y1. So that was something, yeah. Because I think that should be, I don't think it might not be wrong, but I don't like it. So P1 is not going to be this. It's going to be MG. So wait, here's what we're going to do. We're going to do delta Y. It's a terrible name, but it's going to be L1 times 1 minus cos theta 1 of t. Bro, what the hell is going on? Bro, what the hell is going on? So this is going to be, delta y1 plus L2 times 1 minus cos theta 2 of t. Okay, and apparently this is all busted anyways. I know there's something about it being like not relevant what you pick your origin to be. So you could pick straight down to be the origin, I think. But for me, I think I want to do mg, well, m1g times delta y1 and then delta y2. Oh my gosh, why is it so slow today? Like, can't even evaluate individual cells. I'm not sure why. Maybe I've used up my allotment. Yeah, it's not even running any of this stuff. Okay, once I have the Lagrangian that I know is correct, I'm probably not going to derive the equations of motion by hand. I'm just going to use them. And we're going to use this code that I found. What is going on, though? This is insane. Oh, did it run? Is it finally done? What is happening, bro? What the hell? How can I work into these conditions? Fuck yeah. Okay, so it's time to get it into Julia. So first we're going to simulate this system, so let's just try to do that. Try to run the whole thing. Okay. Okay, so did we finish writing the double pendulum? What is this? This is nothing. This one, is this right? We're not going to do the equations by hand, but we are going to. So hold on. Bro. Broski. Oh, yeah. Broski. I'm pretty sure that this should work. So these are the velocity. What happened? Oh, yeah. Where did this happen? Quarks. It's because, oh, yeah. Sloshy. Oh, wait. We had this. Oh, wait. This is old. Yeah. Okay, wait. And I'm gonna, okay. Wait, was it this system? No, okay, this system, we don't need to simplify it. Now we should just be able to go bang, bing, bang, boom. Okay, perfect. So V is the potential. Okay, so these seem to be, so in L, when we're sending this to L is a function that gets traced through. So these are the, so this should be, yeah, what we can do is we can call it omega 1 and omega 2. And then we're going to call it theta 1, theta 2. And then what are our parameters? Our parameters are going to be L1, M1, L1, M2, L2, G. Let's do this here. M1, L1, M2, L2, G. What other parameters do we have? I think that those are the only parameters. Okay. And then T. T was separate, right? You know what? Actually, before I change all this, let's just make sure that this runs. Okay, great. So now let's do Lagrangian double. Oops. Rename. All right. So let's do it. So we're going to have, I'm just going to call it theta 1, theta 2, omega 1, omega 2. Then f of t is going to be nothing. Then we're going to have our parameters. We are going to have gravity. We're going to have L1, M1, L2, M2, and G. Okay, so we have this. Now this needs to be ohm1, ohm2, theta 1, theta 2, and then here, this is just going to be L1, M1, L2, M2. Great. So now we need to write down, okay, so let's just, we should be allowed to do sub-expressions. We don't have to write it exactly this neatly. So the first thing we want to do is we want to figure out what, so like what is V here? Oh, wait, can we go back to the original? What is V? V, okay, V is their velocity. That's fine. So what we're going to get for our potential, which should, I hate the names T and V. T and V are so confusing, especially because V I think of as velocity. Okay, so how do we want to do this? We want to do it like, let's just say, let's just do it the way that we've done it. X1 is equal to L1 times sine theta 1. And this should be of t, right? This is dependent on time. Okay, y1 is equal to minus L1 times cos theta 1. X2 is equal to, and let's leave off Copilot for now, because I just want to think. I don't want to actually, I'm not trying to get something done, I'm trying to learn, you know? Anyways, but it does make things a little annoying. So X2 is going to be X1 plus L2 sine theta 2. And then Y2 is equal to Y1 minus L2 times cos theta 2. Great. The next step is you know what, actually, if we do this out here, let's just see what we can get. Okay, so now if we have, what I want to do is, do we have D? Okay, so if I do D of X1, and I do expand derivatives, I should get perfect. So it does do the chain rule properly. But actually, you know what? I'm a little concerned because so perhaps I should just leave, because we have the simplified version. We have, for instance, that v1 squared is equal to, or v1 squared is equal to, just by doing the algebra manually, it's L1 squared times, this is going to be theta dot 1, so this is going to be omega 1 squared. Right, because the thing is, I don't know if it's going to associate this, because alternatively what we could do is we could just write this manually, that omega 1 is equal to, wait. No. X1 dot is equal to L1 times cos theta 1 times omega 1, right? Because you could do this too, but I don't know about that. All right, then I don't know, we could do that. Well, let's just figure out, what does the full simplify of V2 look like? So if we have a V2 here, or V2 squared, if I did this V2 square, I hate that their servers must be freaking down or something, man. Come on, bro. Okay, so we're supposed to get that V2 squared is equal to L1 squared theta dot 1 squared plus L2 squared theta 2 dot squared plus 2 L1 L2 theta dot 1 theta dot 2 cos theta 1 minus theta 2. I'm like low-key down to just like leave it at that. But then okay, so in the potential energy of this Lagrangian, we see that omega and thetas are used. So okay. I just don't want to do anything funky and have it break. L1 theta 2 squared, 2 L1 L2 cos theta 1. All right, cool. All right, so this is what we're using, bro. So, okay, so we're going to say that V2 squared is equal to V1 squared plus L2 squared times omega 2 squared plus 2 times L1 times L2 times omega 1 times omega 2 times cos theta 1 minus theta 2. Okay, cool. So now our kinetic energy, which is this, I'm calling it K because I'm not insane. Yeah, I said it. Yeah, I said it. All right, is going to be 1/2 times this should be m1 times v1 squared plus m2 times v2 squared. And now the delta y this is going to be L1 times 1 minus cos theta 1. And then y2 from rest is equal to, and it should be y1 from rest plus L2 times 1 minus cos theta 2. Okay? And the potential energy should just be m1g delta y1 plus m2g delta y2, right? So I believe that we should get V is going to be m1 times, or we can factor out the g. G times m1, g times m1 times y1 from rest plus m2 times y2 from rest. Because this is mgh. Now, I don't know, is there a sign issue, maybe? And obviously, because we're not insane, we got the P for potential. So, oh yeah. Kinetic potential K minus P. Okay, now I actually want to call L of ohm1. I actually want to just call this signature, because I named everything the same. So let's just do this. So then if I go L1 is not callable. Oh yeah. That is so crazy, bro. Is there anything else? All right, we have the right Lagrangian. Okay, let's do this thing, baby. Bing, bing, F. I don't know. Excuse me. This is going to, Q is going to be theta 1, theta 2. Q dot is going to be ohm 1, ohm 2. P is going to be, let's make sure we get the right, L1, M1, L2, M2G. Okay, this is going to be double. L, Q dot, blah, blah. Okay. The initial conditions are going to be theta 1, we can leave G. So we have L1 goes to 1, M1 goes to 1, L2 goes to 1, M2 goes to 1, double, I can't tell if that's right. Can we simulate it for longer? This looks periodic, bruh. Okay, so we need to visualize the animation. Oh, theta 2. What happened there? This needs to be faster to animate, bro. Why is it so slow? I feel like there's got to be a faster way to animate this. There's no way it takes this long to animate it. It's because it's making each frame or something. I don't know. Because it's oh, I guess 1,000 frames. It's kind of a lot. Oh. Does it look right? No, this doesn't look right. Yeah, there's something weird going on. Oh wait, you know what we could do actually? I think what we want to do is we want to do solve like this. It should detect the instability or whatever. And then we just want to do save at equals 0.01 or something like this. Because should theta ever go negative? I'm trying to think. Or theta, is that is theta, but I feel like maybe. Wait, what are good initial conditions for? Maybe we should do like. I feel like it looks pretty right. No, but see, like that? What happens there? How is that possible? That doesn't make any sense. Bro, I don't. How do we validate this? Oh, I'm so mad. How do you know if it's right? How do I go? Why would it swing around there? Like, does that really seem right to you? I don't know, it looks pretty accurate, but there is that weird part at 7. Dude, I can't tell, man. I feel like it's right. Honestly, I feel like it's probably right. Okay, so we need to add the generalized forces, but I think the first thing we want to do is we want to get our single pendulum forces down. Okay. Give me a sec. Okay. Why isn't it playing? Why doesn't it loop? You know what I'm curious about? The unstable fixed point. What happens at the unstable fixed point? Let's do... Oh, wait, but we need to do it for the whole time. What is happening right now? Bro, how does that happen? I feel like the physics is right, though. I can't tell. It looks a little finicky. Okay, so let's get back to the important stuff, which is forcing. All right, so we have... So wait, hold on. So let's just... We can delete this. What is this? We can delete this. Okay, we can add... Okay, so we have... We can delete this. What is this? This is... right, we were going to try to do it all like this, but that's silly. That's not going to work. Unfortunately, that's not going to work. Right, because let's watch this video. Does it actually pass through? Because there it misses the ball. I don't know. So that is a problem, right? Like, but if we were to simulate it with, for example, pi over 2, pi over 2. And let's just do, let's actually just do 10 seconds. And then let's just do all 10 seconds. This is going to be 90, 90. So no, yeah. Let's just go back to okay, so I noticed there's okay. I need to go floss. All right, so let's just review the stuff we saw in forcing. So in the README, I have this thing. So let's just review what this whole thing was about. Okay. So first I asked, why is this simple pendulum? It's a toy model because it omits all of the physics you need to describe a golf swing. I hate that the first one it came with was zero moment of inertia, but that's... Torque of T or torque of theta omega. Oh, that's actually interesting. Yeah, could we actually do that? Okay, so let's... So this... Let's just delete that. Harmonic oscillator, let's delete that. Heater, what is heater? Let's delete that. Lotka, let's delete this. Run test, let's delete that. Slope field, let's delete that. It's all in the commit history, so I don't really care. Let's delete that. All right, so we have golf force equations, which honestly I didn't understand any of this because I have a hard time understanding other people's work. I'm sure that this is like pretty good, but we can leave it in here. I can leave discrete event in here just to check. This should go in examples, really. Okay, so we now have double pendulum and golf. All right, so most of these dependencies are garbage. I don't even know what this means. Okay, so it's time to go to the docs. So the first thing I want to know is I want to go to units, and I want units. I want to validate that signing units validate. Returns true if and only if units of equations are valid. So presumably I can just go valid modeling toolkit.validate sys club. Bro, are you serious? I mean, come on, bro. Okay, so why don't we just do validate equations sys club. false. Okay, at least it throws some warnings for me. Units, 1 for left and 1 seconds minus squared. So first off, we want to get rid of this. And we want to do unit t, yeah, so we want to do this. Okay. So we have independent, then we want to do d is equal to differential of t. So, but we probably can't overwrite this at this point. Yes, we need to actually close all of Julia, which is, because Julia just doesn't have a way to clear variables. It's so insane. But that's okay. They're just like, yeah, I don't know. We can't delete anything. You just got to start all over. Now, if this didn't take 5 minutes, you know, maybe it'd be okay, but it's not. Okay. Why is T... Okay, this just shows all the syntax, but it's like... But all of our units should work out now. But I'm guessing that there's going to be some crazy stuff, like... Is it thinking about starting, or is it just going to fucking sit around all day? At the end of this, I'll probably move this to its own repo. Okay, very good. Very good. Oh, MTK build is so slow, bro. It's actually crazy how slow this thing is. Okay. Yes, let's go. At assert. Oh, I love this plot, dude. This is one of my favorite plots. I want to save this plot. How do I save Fig? Has collided. Okay, wait, let's okay, so clean okay, so Lagrangian double pendulum in Joule. Also clean up old files. All right. I mean, it's just nuts to me. Ooh, actually? Wait, this is new. Checks? Wait, what is this not check units thing? I want that thing. How do I do this thing? What is this thing? What is 4? It's just the number 4. What is this thing? Bro, what? How do I use it? How do I use it? Checks? But MTK build doesn't take any of the checks in it, does it, right? Where does it call? So this is the... So wait, we should be able to do quargs then, right? So we should be able to go checks equals... Nah, because see, that's the thing, though. How does MTK... Oh, wait. On our initial conditions... But our initial conditions are just angles, so that's fine. That is psycho, dude. The system type. This is what I want. Where's checks? Checks. What? So system has this checks field, but How come I can't go to this? Where is it defined? Oh, I hate that it just does that, dude. Alright, let's just go to... Alright, this is a waste of my time, but I like... It's crazy because it just like... You see what you want. Whoa, you have to sign in to search code? That's crazy. Alright, hold on, give me a second. I gotta turn off my display. Oh, shit. Um... Alright, sorry, give me a second here. Okay. Check units. PDE system, utils, check units. Why? Bro, what? Okay, I want to see this. I want to see this. So, system type. It does have a checks thing, which is hilarious because it's totally undocumented. Checks equal to true or... So checks defaults to true, so that's good. You get unit type, unknowns, PS. If noise equal to nothing. If IV is not equal to nothing, check units, U jumps, IV. Okay. Okay, so checks should be by default, right? But I don't even know. What does that even mean? Does it throw an error or not? That's goofy. All right, whatever. I don't really care. What we need to do is get back to the torque with respect to time stuff. A realistic shoulder arm muscle torque profile during a golf swing is neither constant nor purely gravity driven. It changes in both magnitude and direction as the golfer transitions from address through the top of the backswing down to impact and through follow through. If you want to replace that arbitrary point +5, Okay, so maybe we should just do something silly. What if I do this? Hold on. So unique. Oh. I don't even understand. How is that possible that it's 113? Oh, no, yeah, okay, it's 113 because that's how many crosses there were. 1, 2, 3, 4, 5, 6, 7, 8. Well, there was something like on the order of 13 crosses. So, but we wanna take a solution. So, anim pend. Okay, so we wanna take cis club. What are the theta and omega? Okay. So okay. Wait, theta. Yeah, because we have to do this. Theta equals cis club dot theta. Then we can do this. Then we can do this, this. Oh, yeah. See how it's like stopping? That's because of these stupid jumps. So what we have to do actually is we have to do this. We have to do t's is equal to unique. And then we can't index. We have to say sol club t's like this. Wait, no. T's is the unique. Then we get this. And then we should be able to get this thing from S. And S should be indexable by theta. Right? Good. All right, so this should be, unfortunately, no, you know what we could do actually? We could just do our T's is equal to the, so wait, hold on. Can we do sol.tspan? Is that a thing? Sol dot prob.tspan. So we have this. So we can just do, and then I think, can't you do lin space range? What does range do? Does range take a step? Or does lin space take a step? Oh, it does. So we can do range. So T is equal to range this step equals 0.01. So now we have the T's, so we don't want these T's. We want these T's. Because the problem is it makes it unphysical. When there's X, there's a jitter, and I don't want a jitter. This we could change, but I don't really care about that. Oh, but 0.01 is stupid. We're trying to do 0.1. And then I want 60 FPS. All right, so this is going to take a while. Wait, interval? What is that? Where is that from? It's got to be like Nemo or something. I've never seen IV syntax like this. So then where is this coming from? Okay, I don't care. DBD, something doesn't look right. No, it looks right. It seems fine. There just seems to be like, it looks like it's hitting a wall, kind of. You know what I mean? I don't know, man. Something just doesn't look right. All right. I mean, the physics are obviously right, but the video doesn't look right. Okay, so now we need to just do something goofy. We want to simulate this where this thing has a freaking +5 in it. And then we want to run this thing again. If we validate this, oh wait. Let's do this. Right, but that's okay. I don't actually care. Okay. That rules. Right, so in this instance, Okay, so let me just, sorry, let's just put a function here. Function anim single pend. All right. And then we just have it take a, we could make this a good function, but we're not going to. I'm just going to give it a name. Okay, so we have this function. Okay, and so what we want to do is we want to now subtract 5. Do this, then we want to do the plot anim, what is it called? Anim single, and did something happen? Oh, okay, no. Minus 5. Okay. So this should now go the other way, right? Wait, but that doesn't make sense. So here, it's because once it's collided, I honestly don't understand. But that is the way that we want it to go. But now what we want it to do is like a sigmoid. So because we need it now, because like at, because presumably what we want to do is we want to do this times has collided. So now let's try to do it again. So it should turn off in sum minus 5. Yeah, so that checks out. All right, so we want to look at minus 5. And it should, what just happened? Why didn't it, why is, because has collided, oh. What? Oh, because you know why? Because this isn't, I gotta be more deliberate, bro. So, we want to stop everything. So, once the collision happens, did I ever find a way to, I did find a way to terminate the system, right? Yeah, you do this. This does work. I'm almost positive that this does work. I'm not going to delete this comment until I verify that, but I'm pretty sure that that's true. All right, so let's run it back. Oh, okay, whatever. So let's, okay. So that seems good. So this is the, all right, so if we were to get rid of everything that we did, which is we're going to So we're going to duplicate this, comment these out, delete all of this, delete this, delete this. So these are the original eeks. Unforced, simple pendulum for reference. Okay, so we can just take these and move this up here. Okay, so if we do this system with no forcing, this is going to be unforced single pendulum. This is just going to be the reference video. So now we want to, so this actually should validate. So if we run this, this, and this one actually does validate. Right, see, we keep getting those assertion errors because we add 5, but 5 is supposed to be something with respect to seconds. Okay, all right, so let's just animate this, but I wanted to know, so, oh, okay, all right. So indeed, this is theta and this is, so actually, I kind of want to change the initial condition. Where do I do that? So I want this to be minus pi over 2. So let's change this thing. Okay, wait, so we have our unforced single pendulum. Great, swings back and forth. So let's start it from there. So this is negative, and to speed it up, we want it to be going in the positive direction. So now we want the plus 5. So hopefully, what I expect to see here is plus 5. So we're going to do a plus 5 just to make sure that, really I'm just trying to get my bearings. And then I expect it to spin around, basically. I expect it to spin around really fast because it's just going to keep, it's going to be, basically, this ends up saying that d theta is exponential. So this should fail now, which is okay because we expect it. Okay, did it run? All right, so we want, what's our new one? It's called forced single pendulum. So here, okay, great. All right, that's what I want because I want it to go, not that it matters, but I do want it to go from left to right. Okay. Good. Okay, let's start reading now about real things. Oh, whoa. Does this still run? Good. Does this still run? Let's see, how do we make it beautiful? Really? Wait. 90 and then 90. That's actually probably pretty accurate. Okay, wait. So where's the Chen paper? I actually kind of hate ResearchGate, dude. All right. Oh, cool. They use basically all the same. I don't include phi, though. Give me a second. I need to download this. Source. No, this isn't .julia dev. Oh wait, yeah, where is it? Math 2B. Even though it's A, right? Test. Let's see. Oh yeah, this is the right folder. Okay, so this we want to be new sources. Can't save this here. Okay, so this looks very good. Holy cow, bro. People go so hard on golf modeling, dude. What the hell? All right, so let's just this doesn't look like the same. All right, let me read this because it's not that hard. Let me take a piss. The purpose of this paper was to examine whether the ball position and wrist action could be optimized to increase the horizontal golf club head speed. To be optimized to increase the horizontal golf club head speed. A two-dimensional double pendulum model of the golf downswing ball position. The simulation results indicated that the horizontal club head speed at impact could be increased by these patterns of wrist action, and the optimum ball position could be determined by the impact criterion. Based on the analysis of the energy flow from input joints of shoulder and wrist, and the way the wrist action affects the club head has been discussed, the sensitivity of the results to small changes in model parameter values were investigated. The results were also examined under different torque patterns. All right. So I should probably read one paper about this just so I have some context. The golf swing is highly dependent on the golfer's wrist action. From the natural release point when the wrist joint turns freely due to the centrifugal torque even though the input torque about the wrist joint is zero, to impact the wrist action is generally divided into three patterns: active, passive, passive-active. Over the years, golfers and researchers have asked the question, which kind of wrist action provide the optimal club head speed at impact? Business study is stroboscopic photography. Williams found that no additional wrist torque was necessary after the natural release point. So, do they cite what natural release point even means? The club freewheeled at the later stage of the Jorgensen and Cochran and Stobbs believe that passive wrist action enhanced clubhead speed at impact. Also considered, clubhead speed could at impact could be increased by the passive active wrist action using a 3-segment model. Confirmed that passive active wrist action can provide an advantage in clubhead speed at impact. However, the golf ball position was assumed to be constant in these studies. I kind of just want to understand the mathematical model. I don't really care as much because like I can't go into all of this. What is this? In the current study, it is demonstrated how the wrist action affects the club head speed from an energy-based analysis. Here, I'm going to kick off a deep research, I think. Do I want to do it here? Yeah, I will. What the hell? Do some research the double pendulum golf model and come up with the quintessential found in the literature. All right, so let's just read this. Mathematical model. As shown in Figure 1, the mathematical model of the golf downswing was deemed to be a two-dimensional double pendulum. This model consists of a rigid arm link and a rigid club link. It was assumed that the swing took place in a plane tilted at an angle phi to the ground. Right. So they actually did this. So this is Chen, right? So Chen did this, where we kind of have a. That wouldn't be too hard to add, but I'm curious to know if it actually does anything. This model consists of a rigid arm length. It was assumed that this is phi, right? To the ground. The assumption of the planar movement is well. So, okay, so use a shifted plane, but the swing still lies on a plane. The downswing was separated into, so we need to write it like this. Yeah. The downswing was separated into two phases. The downswing was separated into two phases. In phase one, two rigid bodies rotate as one body with constant wrist cock angle. Okay, so there's an event that takes place. So during downswing, the first phase holds constant wrist cock. So that means that like so if we have this double pendulum here, so this is phi theta 1 and this is theta 2. And what we're trying to say is that I think it's just going to be theta 2 minus theta 1, right? Okay. In phase 2, the various types of wrist actions were employed. In phase 2, the various types of wrist action were employed. The following notation is, okay, so they have, okay, massive arm and club, massive arm, massive club, length of arm, length of club. I don't really get why they did it like this. Yeah, how you can see it. If you're like looking from above, maybe. What is the target line? Okay, hold on. Length of arm and club, length from shoulder joint to C1. Oh, yeah, okay, so they, okay. Moment, okay, so. Okay. The values of arm and club parameters. Okay, so right, so we could go to LAMPSA 1917. So that's good. All right, so wait, we need to write that down. P values in LAMPSA 1975. So they have, M1, A1, L1. This has got to be L2. It's just no. This is the I, M2, A2, L2, J. What was J? Is this J? Is that a J? That's got to be the J. Okay. So that's the moment of inertia of club. The equations of motion of the model were derived using the Lagrangian method. So, yes. Okay, so there's got to be something. Oh, here, check this out. Interesting. I wish they would just show what the Lagrangian is, because this is not helpful. But I am actually pretty close to this model, which is good news, I wish they would give us the code, but of course they wouldn't. Pretty short paper, actually. Bro, what? It's actually pretty sweet, dude. Oh, all right, the deep research finished. All right, so let's get into it. All right. Bro, Jorgensen is a friggin' beast, man. The central model in golf swing mechanics treats the swinging arms. Central model in golf swing mechanics treats the swinging arms and club as a planar two-link double pendulum. In this model, the upper arm segment pivots about a fixed shoulder joint, and the club pivots about the wrist, both moving in a vertical plane. That's funny. They do it in baseball too.